Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 28. From today we are starting with our selection of design parameters module. In last week we were discussing about very important aspects which covers the flow track design, and we have discussed different kind of configurations which are possible for designing the flow track for axial flow compressor. Let it be LP spool, let it be HP spool. We have discussed about the constant tip diameter configuration, we have discussed about constant hub diameter configuration, we have discussed about constant mean diameter kind of configuration. We also have seen different kind of combinations also possible. This is what is very important when we are discussing the design of axial flow compressor, especially for say industrial compressor, for say aero engine compressor, as well as for say process industry compressors. When we are discussing about the industrial fans, where it may not come into the picture, but still this is what is very important, and that's the reason why we have covered that in last module. Then we were started discussing about the axial flow compressor cascade. So in module 4 and module 3 we were discussing about the design aspects. Now once we have done our all calculation for flow parameters based on our expectation, it is more important to consider different kinds of aerofoils. So in order to have that details, we need to have understanding of different aerofoil parameters. That's what we have discussed with. We have introduced the angles which are known as say incidence angle, deviation angle, metal angle. We have introduced say camber angle, stagger angle, and we also have discussed what all are the importance of those angles, and for design how do we need to calculate those angles. Then we started discussing about different kinds of cascade tunnels which are available globally, and how do we use that data for our design purpose. Now let's start with the next module. So very important part when we are discussing, that's what is coming with the selection of number of blades. When we say we are having gas turbine engines, these gas turbines engines, they are having application for aero engines, they are having application as we have discussed for say power plants, they are having application for the process industries. For all these compressors we need to have certain constraints. Mainly when we are discussing about the aero engines, that's what is very conservative in nature. The reason is we are having so many expectations from those gas turbine engines, and we are looking for those engines to work perfectly. Now when we are talking about those engines application to aircraft, we are looking for, as we discussed, we are looking for say compactness, we are looking for lightweight, we are looking for highly efficient engines with wider operating range. In order to meet such requirements, per stage pressurized expectation that will be increasing. Now when I say per stage pressurized, that's what is increasing, means the stage need to do more amount of work, and that's where our selection of parameter, that's what is coming into the picture. So first parameter or very important parameter, that's what has been defined by Liebling, that's what we have discussed in our module, that's what is called diffusion factor. And that diffusion factor we have realized that's what is a function of my delta beta, that means what is my blade entry angle, what is my blade outlet angle. At the same time we have discussed the parameter called solidity, and solidity we have introduced as cot to pitch ratio. So, the selection of this solidity, that's what is very important. How it is important? Let's see. It has direct impact on my flow capacity. It has direct impact on the efficiency. Also, it is impacting on the stall margin. So, these all are the prime requirements when we are talking about the application part. When we say the per stage pressurized expectation, that's what is to be higher. That means the parameter, what we say solidity, that need to be higher. Now, when I say solidity need to be higher, we know this solidity, it is a function of my chord, and we can say pitch we have defined as a 2 pi r by z. Z is nothing but the number of blades. So now we are having two parameters, that's what is very important for our selection. One, that's what is say number of blades, and second, that's what is say my chord. Okay, when we say chord, that need to have sufficient amount of length. So if you recall, in last module we were discussing about the flow over say suction surface of our aerofoil, and we realized we are looking for all the three regimes of our flow, that's what is laminar flow, transition flow and turbulent flow. So in order to have fully developed turbulent flow on the surface, we need to have sufficient amount of length, that means sufficient amount of chord for that particular blade. Then only we will be having the flow what we are looking for. Suppose say if there is inadequate chord, then we will be having say higher surface loading, that's what will be giving your flow turning to be very large, and that may lead to the flow separation. So here if you look at, suppose this is what we can consider, say here we are having the blade, that's what is having some chord, and we are having say some number of blades, and here if you look at, we are having the height of the blade, that's what is larger compared to say my chord. So if we compare the working of these two, we can realize here in this case my chord length, that's what is sufficient in order to do the diffusion. When we are looking for this kind of blade where the length of the blade or height of the blade, that's what is larger, it may be possible that my chord may not be sufficient, and that's where it may be possible that we need to have consideration, design consideration that need to come into the picture. We can say the flow passage, we should not forget all what we are discussing, that's what is a diffusing passage. Okay, so let's try to understand what all we are knowing and how do we use that knowledge. So conventionally in past, people used to select say even number of stator blades and prime number of rotor blades. So that's what was not that logical in that sense, but based on understanding, based on study, they have come up with this kind of configuration. Now the thing is, when we are talking about the prime number of rotor blades, in case of one of the blade, that's what will be fail, then we need to replace that blade, and that's what is required, say maybe balancing again, and that's what is time consuming process. If we are considering application for aero engines where time also is a major concern. So in order to address this kind of issues for say high bypass ratio fans, these fan blades, this aircraft or airline companies, they are procuring in a set. So suppose in case of failure of one of the blade, that's what will be replaced on both the side, and that's what will be saving their time in sense of balancing. So as such there is no specific rule in sense of selection of number of blades, but we will discuss like how people they are understanding for the selection of number of blades, because that's what is very important when we are looking for other aspects. As we have discussed what chord we are selecting, suppose if we are talking about the first stage, then I need to have sufficient length of that chord so that we will not be having any damage or say foreign object that's what will be striking on that blade. It should have sufficient strength. So all these things, that's what is giving the indication in sense of what need to be by chord and what need to be by number of blades. Here if we consider say number of blades, then we need to realize what kind of loading we are looking for. That means per stage loading what we are expecting. Second parameter, that's what is coming into the picture, is a weight of that rotor, and because of the weight of that rotor, the weight of whole engine. Then we will need to check for say manufacturing cost, and we need to compromise in sense of all these parameters. Let me put it here. Suppose if we are talking about say industrial compressor which we are using for say power generation purpose, there we are having major concern, that's what is the cost. There we are not having any constraints in sense of length of my engine. So under that configuration, your selection of number of blade, that's what is not playing that major role. Okay, we can increase the number of stages, but when we are talking about the aero engine application where we have restriction with the length, okay, under that condition we need to play with all these parameters, that's what is say blade loading, weight, as well as the manufacturing cost. So Liblin's parameter, that's what is giving us idea in sense of solidity, and based on that, as we have discussed, these days people they are taking this as one of the parameter. So mainly at tip region, the diffusion factor they are assuming. Based on that assumption, they are selecting the number of blades. Now this number of blades, that's what will be decided with, and then they will move ahead with the design modification. Maybe they will stick with the same number, or maybe based on computational study, maybe they will be modifying those number of blades. But it says we need to take care of other parameters also along with the diffusion factor. That's what is taking care of our secondary flows. They are say tip solidity, then tip and hub Dehaulers number, and static pressure rise coefficient. So there are so many parameters which are coming into the picture when we are discussing about the selection of number of blades. Okay, so for first cut design, for the initial design, it is the best way to select your diffusion factor or assume your diffusion factor, and you can move ahead. As we will move ahead with the discussion in next module, we will be discussing what all are the other possibilities also for the selection of number of blades. But at this moment, just realize, say diffusion factor, that's what is giving me the understanding of what kind of loading or what type of loading we are expecting from particular stage. Okay, so blade number, that's what is a compromise between your operating range as well as your efficiency. Now it says one must have enough number of blade to ensure the stall margin, but not too many blades, that's what will be giving the detrimental effect on efficiency and manufacturing. So there it says you need to play with these numbers. Okay, it says the train for increasing the solidity in relation with the increase of the stage loading, that's what is expecting some new kind of thought process. Let me tell you, say new concepts like tandem configuration, aspirated vanes, active and passive flow control mechanism, etc. Now we need to introduce. It may take time, but yes, this is what is now new demand. Okay, and that's what will be helping us for addressing the few of the issue which we are discussing in terms of margin as well as in terms of say efficiency. Okay, now here if you look at, we are having, do not get confused with the parameter here. This is what we are discussing in sense of radius ratio. Suppose if I consider this is what is my hub to tip ratio as 0.8, and here in this case we are having our hub to tip ratio as 0.4. So we can say when we are having hub to tip ratio, that's what is say 0.8 means we will be having shorter blades, mostly for rear blades or rear compressor blades or of this kind. When we are discussing the front stage or maybe for fans, they are having this hub to tip ratio, that's what is in the range of say maybe 0.4, 0.5. Okay, now here this is what is representing. Suppose if I consider say we are having 12 number of blades. Okay, and suppose if I am considering, that's what is having say height to chord ratio, that's what is say 1. Okay, now we are having the possibility, as we have discussed, we would like to change our solidity, or we say we want to increase our solidity. When I say we are looking for increasing the solidity, then we are having two possibilities. One, it is to increase the chord. Second, that's what is to increase the number of blades, or maybe you can go with both. But when we are going with both, you need to have compromise somewhere, and that compromise, as we have discussed, that's what is on our stall margin as well as on our efficiency. Here if you look at, again, do not forget, this is what all we are discussing in sense of making the diffusing passage. So here if you look at, we are having 12 number of blades. We will be going say little conservative and say we will be reducing the number of blades, but remember, by reducing the number of blades, my passage area, that's what is going to be large, and it may not give what pressure we are expecting. Okay, so the next option, that's what will be coming with the increase of number of blades. So suppose here we are increasing our number of blades. Yes, this is what will be giving you high pressure rise, or what pressure rise we are expecting. But because of presence of more number of blades, the losses are going to increase. Those losses are frictional losses because of presence of more number of blades, and that's what will lead to reduce your efficiency. Okay, now here in this case, suppose if you consider, say here we are having our up to tip ratio in the range of 0.4. Okay, so here if you look at, if I am putting my chord as constant, okay, so chord as constant, and if we are increasing our number of blades, then you can understand, by increasing our number of blades, we are making our diffusing passage to be narrower, and that may give higher pressure rise. Okay, but we need to realize one thing, what chord length we are selecting, that's what is very important, because your chord need to be sufficient to sustain your flow on the suction surface. We have realized all kind of flow physics, that's what is happening on my suction surface, and that's what will lead to change my CP distribution of that particular aerofoil. When my CP distribution, that's what is decreasing, you can say my pressurizing capacity at that particular station, that's what is decreasing. In overall, we can say there is a reduction in pressure rise, okay, by that particular rotor, or say rotor and stator combination, or say for stage. Okay, now let's see the other parameter, that's what is coming into the picture. People, they started talking about the aspect ratio. So here in this case, this aspect ratio, suppose if I consider say my radius ratio of 0.8. Okay, so be careful, as I discussed earlier, my radius ratio and aspect ratio, they both are different things. Remember, we can have our radius ratio to be same, but we will be having blades with different aspect ratios. So here in this case, if you look at, this aspect ratio is defined as height of the blade to the chord of the blade. Okay, so here in this case, if you look at, my height is higher compared to my chord, we can say that as a high aspect ratio blade. When I consider say my height to chord ratio, this height of my blade and chord, that's what is say lower, or my height of the blade, that's what is lower, or I say my chord of the blade, that's what is larger, we can say that as a low aspect ratio blade. Okay, now this aspect ratio, that's what is very important for say our axial flow compressor, what we are using specially for aero engines. Okay, here in this case we are focusing, or our major focus, it is on three parameters. First, that's what is with the aerodynamics. Second, that's what is with the mass, and third, that's what is with your say mechanics. So when we say we are having this aspect ratio, so low aspect ratio blade, that's what is giving benefit in sense of stall margin, and that's what is increasing my overall operating range. let me tell, this overall operating range is nothing but it's a region from maximum mass flow rate to minimum mass flow rate. Okay, that's what we say, it's an operating range. Okay, so when we are having say low aspect ratio blade, that's what is giving us good stall margin, it is giving us higher operating range, but we need to compromise in sense of efficiency by few points. Okay, we will see what is the reason behind that, but you can understand this lower aspect ratio blade, that's what is having this kind of benefits. Suppose if I am talking about say mass, okay, so for a high aspect ratio, it will reduce the length of my compressor. So you can understand, suppose if I consider say high aspect ratio blades, that's what will going to reduce my overall length of the compressor. That means that's what will be helping us in reducing our mass. Okay, and next parameter, that's what is with the mechanics. If you consider say high aspect ratio blade, you can understand my blades are taller blades, and that's what will lead to give the focus of my stresses and vibration. It is having issue with the aeroelasticity. So before 50s and 60s, most of the compressors or most of the engines, what we are looking for, they are having the high aspect ratio blade. Later on, people they started talking in sense of low aspect ratio blade. There are major contribution by Whistler, there are major contribution by say Westlers. Okay, so they have explored the possibility of using low aspect ratio blade, and that's how this low aspect ratio blade that has come into the picture. Because you can understand, again and again we are saying our major concern is with the safety, and when we are saying say safety, that means we are looking for broader operating range, we are looking for say stall margin to be slightly higher. So under that configuration, we need to think in sense of low aspect ratio blades. Okay, now let's see what all we learned for so a low aspect ratio blade. What it says, when we are having say low aspect ratio blade, then it will be having higher blade loading, and according to Koch, it says we are having, so suppose if I consider this is what is representing my low aspect ratio blade. So the tip clearance, that's what we are defining in sense of T by H. We can say that's what is the function of my height of the blade. So tip of the tip clearance by chord, that's what will be coming to be lower in that case. Okay, and again when we are looking for say having wider chord, that's what is increasing the Reynolds number. Okay, when I say it is increasing my Reynolds number, that's what will lead to give my flow to be more turbulent on the suction surface and on the pressure surface, and that's what we are looking for. Okay, and that's what is helping us in sense of minimizing the chances of flow separation. When we say we are minimizing the chances for flow separation, we are minimizing the chances for stall, and that's how we are improving our stall margin. Okay, also lower axial pressure gradient in the casing boundary layer, that's what is a benefit of low aspect ratio blade. And most importantly, people they started talking, it is more robust to ingestion and erosion problem, because we are having our blade thickness, that's what is larger. So just understand, when we are discussing say aerofoil, the maximum thickness, that's what we are always defining in sense of chord. We say T by C ratio. So when I am increasing my chord, then automatically the thickness of the blade that will be increasing. That's what will lead to improve the thickness or say my radius at the leading edge. Same way it is improving my radius at the trailing edge. So all this, now since we have understanding of compressor blade and compressor cascade, all these things we can correlate, and that's the reason why module 4 it has been designed such that it will give more clarity for this kind of discussions. Okay, Some of the mechanical disadvantages of this low aspect ratio blades, they are increasing the stress because of mass increase. So you can understand, since we are increasing our chord, that's what will lead to increase the mass of my rotor, okay, or mass of my stator, okay. Next, that's what is the excitation potential due to the decrease of relative axial gap. So the axial gap between rotor and stator, basically we are deciding based on percentage chord. So that's what is always a proprietary nature kind of work, but conventionally people, they are defining the axial gap between rotor and stator as percentage chord of rotor. Sometimes they are considering, say, percentage chord of average of chord of rotor and chord of stator, okay. And there may be possibility that blade off, that's what will be taking place, okay. So now when we are discussing low aspect ratio blade, we are having special kind of requirements for our case, okay. Now here in this case, if you recall, when we started discussing about, say, engines, that time I was showing one of the engine, that's what was Pratt & Whitney engine. I was showing one more engine, that's what was, say, GE Honda engine. And if you recall, I was discussing for new coming engines, people, they are talking about wide chord blades. That's what is because now our expectation in sense of operating range is increasing, okay. Now if you look at, this is what is a global train. So here if we consider, say, this is what is representing in 50s and this is what is during, say, 2000, and again that's what is continue to get converged, okay. It says my trend for last 50 years, that's what is to reduce the aspect ratio, okay, because we are looking for enhancement of stability, we are looking for more and more highly loaded compressor, because we are looking for reducing the number of stages, okay. We are looking for, say, compactness, we are looking for the lightweight, okay. So the increase of stage loading, and that's the reason why reducing, say, number of stages, that will be compensated by decrease of aspect ratio. And when we look at in global sense, that's what is reducing the length of our compressor stages, okay. Now this is what is one of the work, that's what is been reported by University of Cambridge. Now whole concern, that's what is how do we, or what need to be the aspect ratio. So for that case, what they have done, they have taken two different aspect ratio blades, they are having same thickness and same clearance, okay. So here if you look at this clearance and this clearance, that's what is same, and the thickness of the blade also they have considered to be same. Now earlier people, they were, say, judging, they were giving the reason for the selection of high aspect ratio blade, that's what is giving benefit in sense of reduction of end wall losses, and yes, that's what is, okay. But if you look at here, this is what is a reported work. What it says, when we are increasing our aspect ratio, we have our end wall losses, that's what is going to reduce, but at the same time our profile losses, they are going to increase, and this is what it says, loss of efficiency. So we will be having, say, optimum range. Here this is what is coming 1.15. Authors, they are recommending, say, 0.8 to 1.4, that can be the optimum aspect ratio, okay. So if you recall, in last lecture we were discussing about the profile loss, so you can correlate what we mean by profile loss here, okay. So this is also one of the indication why we are moving towards the low aspect ratio blade. Now just look at this is giving what all we have discussed today. Now if you look at, this is what is representing the global trend. So here if you look at, say, in 30s and 40s, our expected pressure ratio was less. As per our requirement, that's what has increased. Our expectation in sense of transport purpose, that's what has increased our pressure ratio. So you can say over the year, pressure ratio is almost reached to 40:1. For most recent engine, the pressure ratio has reached to 64:1. Okay, so over the years, our expected pressure rise, that's what is increasing. At the same time, what we are looking for? We are looking for, say, average loading. Per stage loading also we are getting improved. So here if you look at, we are expecting per stage pressure rise to be higher and higher. Okay, that's what is, say, over the year, that's what is ranging on higher side. And if you look at, this is what is representing, in order to meet these two requirements, we are looking for higher solidity of the blades. So this is what is representing, we are moving towards higher number of solidity. Okay, and at the same time when we say solidity, that's what is correlating our chord and number of blades. And if we look at, this is what is representing the trend for aspect ratios. So over the year, people now they are preferred to move with, say, low aspect ratio blade, and that's what is again and again, that's what is getting converged. So looking to this global trend with the expectation for future, we are looking for such kind of configuration. Do not forget, say, design of, say, axial flow compressor, that's what was started long back. People, they have done all kind of designs. It is not that that's what is the end of story. This particular plot, that's what is giving you idea how people they are thinking for future development of engines. What all parameters they are playing with in order to meet specific requirement. Now when I say specific requirement, just look at here. This is what is our requirement. What is our requirement? We are looking for our thrust specific fuel consumption to be lower. So if you look at during 60s, we were looking for, that's what we have taken as a reference. The next expectation, that's what has said, like, you need to reduce the thrust specific fuel consumption by 15%. That's what has given the new concept, that's what we say twin spool configuration. Later we are looking for reduction in thrust specific fuel consumption. It gives the idea about, say, having turbofan kind of configuration. Later on, people they are talking about high bypass ratio kind of configuration. Then again people they started talking about, say, turbofan or prop fan kind of configuration. Let me tell you, at recent people they started talking about ultra high bypass ratio engine. So this is what is running the whole business for gas turbine industries, specifically for the application of aero engines. Now let me tell you what all people they are working for aero engines. Slowly that's what is being implemented even for land-based power plants, because there also our fuel consumption is of major concern. People they are looking for low cost engines, that's what will be giving, say, good improvement in sense of fuel consumption, and we are having restrictions with the pollution norms. So in order to meet all such requirements, we need to have whole lot of research and development. Still that's what is pending, and we need to focus for the future. So this is what is the end of our lecture. We will be discussing the next step in the next lecture. Thank you very much.